Hey everybody, Mr. Brooks here again. So today we're going to go over section 3.11, which is higher order linear, homogeneous, ordinary differential equations. So I didn't want to write up the whole entire thing, but that's exactly what this means. So lately we've only been talking about first and second degree or second order differential equations. And so we're going to see actually everything that we have talked about in the previous sections can be extended to higher orders, so the third order, fourth order, and so forth. So again, everything we've covered for second degree or second order ODEs. So everything we cover for second order equations can be applied or developed to higher order. So the first one we're going to look at, and I went ahead and wrote this out because otherwise you'd see me writing this for a while. So the first thing that we can talk about is the existence and uniqueness theorem. This is very similar to what we talked about with first order and second order differential equations when they're dealing with homogeneous. So the nice thing about this one, because we are dealing with, we'll be dealing with linear equations, we are allowed to talk about the existence of a unique solution. So here, this is going to be an arbitrary or a generalized form, but we have y to the nth derivative. So when we put parentheses around numbers, we're no longer using the prime notation. So as you can see, this is an nth order differential equation. So this is the nth derivative. This is the nth minus 1 derivative and so forth up to first derivative and then the original. And then we have these multiplying functions of t starting with p sub n minus 1, so it's after the first term because we generally leave this reserved to have a coefficient of 1. So everybody else has a function of t attached to it. All right, here our conditions are that every single one of these functions of t and g of t must be continuous on some interval ab containing our value of interest, t sub 0. Then the initial value problem, again dealing with our generalized form here of an nth order differential equation. And this is where the fun part becomes. So if we have an nth order differential equation and we're dealing with the IVP, we have to have n minus 1 initial conditions. So this is what these values are talking about. So we evaluate it when y, we're dealing with the original function of y, and then the derivative of y, and then all the way to the nth minus 1 derivative of y, evaluating at t sub 0. So again, with the second order, we always had 2 conditions, and so with the first order, we had 1 condition. So with an nth order, we have n minus 1 conditions to go with it. All right. So this has a unique solution on the entire interval from a to b. So this is the cool thing. We can guarantee the existence of a solution given any IVP. How we get to that solution is a different story, but we will talk about that in section 3.12 and actually starts off. So this section is just an intro section. So there's going to be more definitions and theorems coming out from this section than there are going to be going through problem solving. So again, this is those intro sections like what we had at the beginning of chapter 3 and the beginning of chapter 1. We're just introducing all of these. So again, the existence and uniqueness theorem allows us to say, hey, once we get a solution, this is the only solution on that particular interval. All right. So next step is going over talking about fundamental sets. In order to talk about fundamental sets, we need to talk about one thing in particular. So let's consider our nth order linear homogeneous equation. So notice I shifted it over. Here we have the same equation as in 1, but except g of t now is 0, so we are dealing with homogeneous. And I've labeled this equation 2, and I normally don't do that but because of the length of writing this out, and also because we're putting this into videos, I'm going to reference back to this one several times. So when I talk about equation 2 for the rest of this video, I am talking about this guy in particular. So the superposition principle we have seen before. So what it means is the linear combination of solutions of the homogeneous again, equation 2 here, and I'm going to go ahead and say that's equation 2 that we've talked about, this guy right there. So the linear combination of solutions of the homogeneous equation is also a solution. So we have seen this before, and that's actually how we generated those complementary equations at the beginning of this chapter. Okay, so again, the linear combination of solutions of the homogeneous equation is a solution. All right. In other words, another way to state this, if y1, y2, y3, y sub n are solutions to 2, again referring back to this equation here, if they are solutions, then y sub t is equal to c1y1 plus c2y2 plus so on up to c sub n y sub n. So again, a linear combination is also a solution to 2. Okay, so that gets us into talking about, well, if we're dealing with a linear combination, there's one thing that we need to check, and this is the fun part, and also, well, I wouldn't say the fun part. This is the more tedious part of this chapter, or this part of the chapter for chapter 3, is dealing with, well, how do you confirm that a set of solutions are linearly independent of each other? Well, they're Wronskian. So this is where we're going to talk about forming a fundamental set. So assume, you all know what that means, assume that the set of solutions here, y1, y2, y3, to y sub n, is a fundamental set of solutions. Okay, so we know what a fundamental set of solutions are. They're linearly independent of each other. Okay, of equation 2, again, that guy over there, where we're dealing with the homogeneous, satisfying the non-zero Wronskian. And how did we find that non-zero Wronskian? Well, we said that W of t, the Wronskian, is equal to the determinant of, now, this massive, because we're dealing with higher order, so we're no longer dealing with just 2 solutions. We could have multiple solutions for these guys. So if we have a 3rd order, we're going to have 3 solutions. If we have a 4th order, we have 4 solutions, and so on. So to generalize this, we get y1, y2, up to y sub n. So we have all of the original solutions here, and then we have our row of first derivatives. and then all the way down to the n-1 derivative. And again, putting parentheses around our number indicates that we are dealing with a derivative. So our n-1 derivative. We want this to be not equal to 0. Okay, so this is where a lot of painstaking algebra is going to come into play, because you're going to be dealing with what we call minors for calculating the determinant. And so with a 2 by 2, we just multiplied the diagonals and then subtracted the 2. Well, with minors, I'll give an example in section 312. So to demonstrate how to go through those, and I'll also deal with a 4 by 4 just one time, because otherwise that becomes very lengthy to deal with. So I'm just going to show it one time for that part. But they're not bad. It's a pain in the butt sometimes to deal with those guys. All right. So provided that this occurs, again, we're talking about a fundamental set, then any solution y of t can be expressed as y of t is equal to c1 y1 plus c2 y2 plus so on. So again, this is just reinforcing our idea that we talked about, the superposition principle. So this is just an extension of this, using the Wronskian to talk about them being linearly independent of each other. So that's the big case. So again, a fundamental set is those solutions that are linearly independent, meaning the Wronskian is not equal to 0 in that case. All right. So next we're going to talk about a couple of useful theorems that we have out here. So the first one that we're going to deal with is called Abels Theorem. And again, there's a more technical writing of that particular theorem. But I'm going to give you the quick rundown of it and deal with an example as well. So this is Abels Theorem. Abels Theorem is really cool because instead of dealing with the Wronskian for dealing with all values of t, so where we have to prove it for all values of t, Abels Theorem can be used to talk about, well, we just need to evaluate it at one value of t, which means I can use numbers instead of having to go through every single one of those derivatives and then write them out. Yes, I'm still going to have to find them, but then I get to use the values of those derivatives instead, so I'm just dealing with straight up numbers, and then I can add and subtract those guys a lot easier than I can talking about multiplying like sine and cosine and whatnot. So Abels Theorem has that extension. So first of all, we're dealing with the Wronskian. W of t, by definition, is the Wronskian. So the determinant of the fundamental set y1, y2, y sub n. Again, these are solutions. So let's write that, the fundamental solution, or fundamental set. To, or of, let's say of, equation 2. Again, referring back to our equation there, that's why I didn't erase this side of the board just yet, because I'm going to refer to a couple more times. So again, the W sub t is the Wronskian, so this means since it is from a fundamental set, the Wronskian is not equal to 0. So then, if that's the case, the Wronskian, that function that we talked about, is a solution of the linear differential equation w prime, which is equal to negative p minus 1 of t times our Wronskian. So what this is saying is we take this function of t here. So if it was 0, if there was no n minus 1 term derivative in here, if it was 0, then this guy would be 0 here. So if this is some function, we could say it's e to the t, then I'd have negative e to the t here. And I'll give an example here in just a second of using this. Therefore, so if that's the case, this is a solution to this particular equation. Therefore, if t sub 0, the initial value, is any point in our interval of interest AB, it follows that W of t is equal to, so the initial value, E, so again, this is coming from the solution here, okay? So if we had solved this for W, so if we found the solution to this guy, this is where it's coming from. So this is what we're generating. E to the negative, now this is going to be a little bit different. The integral from our initial value to t, there's a reason why I'm putting t here, of p of n minus 1 of s ds. So what we're doing is we're evaluating this from the initial value to t, so this is going to become a function of t in this exponent, so it's a little weird when we look at it that way. All right, so that being said, let's look at an application of this. Right? So again, this is showing, or it can be used to talk about finding the Wronskian for any value of t in that interval. Okay? So an example of this being used is if we have y triple prime, so we're dealing with the third order here. So I have a third order plus t over 2 y prime plus y is equal to 0. Again, dealing with a homogeneous linear here. And we know the Wronskian evaluated at 0 is equal to 1, so it's a non-zero there. What is the Wronskian evaluated at 4? Well, if I don't know what my values are, how can I deal with this? If I don't know what those solutions to that particular differential equation is, how do I find out that Wronskian? Well, this is where Abels Theorem comes into play. So we can actually use this to find out what the Wronskian is evaluated at 4. So for us, W sub t is equal to W sub 0, so where we evaluated it here, so we're going to plug 1 in here in just a second, e to the negative integral from 0 to t, okay, of, well, our p sub n minus 1, okay. Notice that we're missing the second order here, okay, so there is no second derivative in this equation. Its coefficient was 0, so therefore, we plug in a 0 here, ds. All right, well, the integral of that guy evaluated as 0 is still 0. It's a constant. So in this case, we're going to get W sub 0 times e to the 0, which is just going to give us the value of 1. Again, writing up from this part, since y double prime does not exist, or does not appear in our equation. All right, so therefore, W of 4 is also equal to 1 for that case. So the nice thing is if we did have, say that we had y double prime in there. So I'm going to make an adjustment for this. All right. If we had, so same conditions, and I'm going to say that what if we had now y triple prime plus t over 2 y prime plus y is equal to, sorry, lift off the double prime plus t over 2 y prime plus y is equal to 0. Then same conditions, what would happen if we get w when we apply this at 4? So w sub t would equal w sub 1, so I'm going to go ahead and plug 1 in there, e to the negative integral from 0 to t of 1, because that is the coefficient out in front of here. So it'd been a function of t, it could be a constant, whatever it happens to be. All right? And sorry, this is ds here. So we're going to get e to the negative integral, or not negative integral, but to the negative s, evaluated from 0 to t. Well, if that's the case, we're going to get e to the negative t minus 0. So therefore, we get e to the negative t. So that means w of 4 is going to equal e to the negative 4. And that would be the Wronskian's value. So this is how we can apply Abels' theorem. And so Abels' theorem allows us to evaluate or be given function values, so initial conditions, and we can actually determine if it was linearly independent or not. And so if the determinant is not equal to 0, then we don't have a fundamental set and can't solve. However, if we do, then we can solve with it. So that's the cool part about it. So if you're given initial conditions, you can check the Wronskian of those values and determine if you actually have a fundamental set at the beginning or not. All right. Another useful theorem that we have out here, and this is our last one that we're going to cover for section 311. And I'm going to call this useful theorem. And it's kind of adding on the idea of Abels' theorem that we've already talked about, but it's just reinforcing it. So we're going to let, I'll go ahead and erase this too, so that is all the way out of the way, and there's no issue here. So we're going to let y1, y2, y3, and so forth be a set of solutions of, and I'm going to write this one out again. So this is our equation 2. Again, if we refer back to this, this is equation 2 that we talked about at the very beginning of this section. So if we have that this is a set of solutions for this nth order differential equation, homogeneous equation, where p sub I of t, okay, again, here I goes from 0 to n, sorry, n minus 1. If these guys are continuous on AB, then the following are equivalent. Okay. So once we have these terms here that we have the set of solutions for a homogeneous nth order differential equation where the coefficients are continuous, then the following statements are equivalent. Number one, this means that the set of solutions forms a fundamental set. Of solutions to 2. Which means that we can use the superposition principle to talk about some linear combination. Number 2, that means if these guys are a solution and they form a fundamental set, well, if they form a fundamental set, what does that mean about the Wronskian? Well, that means the Wronskian, W sub t, is not equal to 0 for all t on AB. And number 3, applying Abels Theorem, that the Wronskian evaluated at some value of t is also not equal to 0 for some, and this just means for a select value, for some t sub 0 on AB. Okay, so again, this is talking about a specific value of t. This is talking about for all values of t, which if we're given a set of solutions and we said, okay, find out what the Wronskian is for a specific value of t, we can do this. And applying Abels Theorem if we wanted to talk about other values of t. Here, if we wanted to be more generalized, we could say that the Wronskian is not equal to 0 for all values of t if this forms a fundamental set. So that is all we're going to cover in section 311. So again, this was more talking about theorems and definitions that we'll be applying later into 312. And 312 is where we're going to actually talk about how we solve these guys. Mostly it's going to be talking about, and this is the part you're going to love, we're going to be dealing with finding out the determinants of 3x3 and 4x4 matrices. We might even have to use a calculator for that, which is good. We can still do that. And also think about the characteristic equation. We're no longer dealing with a quadratic, which means we're going to have to deal with factoring. And how are we going to deal with factoring? Well, probably synthetics division of some sort is going to pop up with that, or factoring by grouping if we're allowed to. So that's all we're going to talk about today. And so that covers section 311.